Hi, I'm Liz. I probably should have titled this talk something less fancy because basically I'm talking about taking open source projects and porting them to various architectures and the tools and things you have to think about when you're going about that. But the first thing to know about me, I am incredibly biased. I work on mainframes. So if you come up to me later and ask me a question about an architecture, I'm going to know more about the IBM Z architecture because that is what I work on at work. Not these ones. Although, fun fact, this is an IBM 360. It's kind of like the first modular kind of modern computer mainframe thing that we can think of as what we'd call a mainframe. It was launched 60 years ago tomorrow, so yay, 360. But I don't work on those. I do have a masthead from one of those in my home office because I thought it was cool and I found it on eBay. Don't let me near eBay. But I don't work on these ones. I also don't work on movie mainframes. I'm gonna get in trouble for this slide. But I just saw Argyle a few weeks ago, and that one has a scene in it where there's the climax and they go and they have to hack the mainframe and stuff, and those don't look anything like what I work on. I work on this. This is an IBM Z mainframe, but this one is made out of Lego. This one is made out of 250,000 Legos. IBM actually commissioned Lego Master Builder to build a scale model. It's pretty amazing. I wrote an article about it when it came out, not because I had anything involved with it. I heard we had a Lego mainframe at a conference, and I'm like, oh my gosh, who do I have to talk to about that? I have a mini one in my backpack I can show later if anyone wants to see the little baby mainframe, but it's not assembled because I ran out of time. Anyway, Lego mainframes. Okay, but this is for real. This is what I work on. So mainframes these days, they're smaller than they used to be. They fit into a 19-inch rack spot. We have rack mount versions, which just came out last year. So it's I think the smallest configuration is something like 16 or 20U, and they can fit in an industry standard rack with a bunch of requirements. You need a special forklift for them and all kinds of stuff. But the ones with doors, they can be anywhere between 1 and 4 frames wide. But they're very modern things. We come out with new ones all the time. So every couple of years, 2 or 3 years, there's a new model that comes out. So these are not old things. The other thing you should know about this talk is that I am going to focus on Linux development because that is what I'm familiar with, and that is primarily what I work on. I am getting more familiar with the IBM proprietary stuff and the ZOS side of things, and my job role actually encompasses both Linux and ZOS in my leadership of the open source program office for IBM Z. But in this talk, I'm specifically talking about Linux. I'm not going to talk really about microcontrollers, although I will mention them, or embedded systems that don't use Linux, because open source projects on those are a little bit different than what I'm familiar with. I also grabbed this quote from a friend of mine while I was prepping for this talk, and he's like, I think it's safe to say that once a new weird platform gets full Linux support, it's mature enough to use. So the ones I'm going to include are also mature enough to run Linux. The other thing to note, I spoke at CPOSC in 2009. I was younger, I dressed better, I worked at a startup, now I'm older, I dress like this, and I work at IBM. So I don't know how that happened, but I think I thought this would bring me more credibility, but just being myself turns out that actually works better than trying to dress up and be uncomfortable. And I had a different name back then, so. Anyway, so the architectures I want to talk about today are these 4. So if you're a hardcore architecture geek, you're going to notice some things missing from this list. I didn't include MIPS on here because the status of MIPS is kind of in a weird spot at the moment. You may say, well, technically ARM is a RISC processor, and then you specifically call out RISC-V, but they're different things. And in the realm of talking about open source software on Linux, these are primarily what you're going to see. So when you talk about ARM, in the open source world, you're going to see it referred to in binaries. When you go to download things, it's going to be either AArch64 or ARM64 in the little side thing. IBM Z or Linux One is going to be referred to as S390X. Power is going to be PPC64LE, and I'll deconstruct these a little bit in a moment. And then RISC-V you'll see around as RISC-V64. I'm also not touching 32-bit at all, but if you wanted to run the 32-bit version or build it for your open source software, in the world of ARM, you'll either see it just as ARM or ARM32. In S390X, you probably won't see it. It also wasn't 32-bit, it was 31-bit. But usually you would just see it as S390 without the X. PowerPC comes in a few different versions. So it used to have BE at the end, and that meant stand for big endian. LE is little endian, which is endianness is a way of doing memory addressing. But pretty much everything on the market for power is now little endian, just like everything else, except for S390X. And then RISC-V, I believe it's only 64-bit. Maybe I'm wrong. And then the way you kind of see these in the world is for ARM and RISC-V. They're very commonly found in microcontrollers, embedded systems, but they also have them in desktops and laptops and servers. So, the new Macs are ARM-based. I actually have some fun little props over here, and you can come over and ask me to see them later. So this one is a RISC-V SBC. It's a single board computer, kind of like a Raspberry Pi. It's got a couple of HDMI. It has one HDMI port, 2 Ethernet ports, and this one runs Debian. At least it will, again, when I unbrick the firmware. Oops. I was flashing it before I came here, and it went wrong. The other little things I have over here, we can take a look later. If anyone wants to come see me later, they'll be in my backpack. This is a mainframe. Look how small. No, I'm just kidding. It's 3D printed. The 3D printer files are available online. I'd put the RISC-V in here, but then I'd really get in trouble. I got a little Linux Power Penguin here. And I was like, oh, what do I have for ARM? Oh, I'm wearing it, right? Like your watch. This is a Pixel 2. It's ARM processor inside a Cortex ARM processor. Phone, your Android phone, it's an ARM processor as well. So I didn't even need to bring those props. They are always with me. So I have all the architectures here. So that's what we're going to talk about. Oh, and I put these in alphabetical order, and that's going to go for everything in my presentation pretty much. So I don't play favorites and I don't get in trouble. I'm also not going to talk about why you would necessarily use one server over another or one microcontroller over another. Because one, I don't have the expertise to do it, and two, it doesn't matter. That's not what the talk's about. So it was analysis you'll have to do on your own. So the first question I often get, why do these hardware architectures exist? Why are there all these weird things out there? So the first thing I like to think about is, how did we get to a place where we just develop open source software for one architecture? Prior to this, we had all kinds of things. In the 90s, there were a lot of different architectures out there. I have a Spark Ultra 10. That's the Spark 64 architecture in my home office. It's almost running. I had to replace the hard drive and some other little things, but it's almost there. But that's an architecture you don't see anymore, and there's not a lot of support for it out there. But back in the day, there were all these other architectures. That's the banner I talked about from the 360, and that's actually my RISC-V board, all connected to its serial to USB thing and the Ethernet and all that, back when it ran Debian for a few minutes before I broke it. But some of the things to think about is, as we're moving forward in time, there was a time, early 2000s, where it was really easy to just take a bunch of x86 servers, stash them in a data center, and be like, we're going to run everything on it. If we need more, we add more servers. All is good. But workloads are changing. People are more power conscious these days. There's a lot of different form factors now. And I'm actually going to exit my slide deck because I saw the coolest thing the other day. I was at the IBM office in Poughkeepsie. This is the heat sink for the air-cooled mainframe processor. It's very big. You can't put that in your phone. So, size is obviously a big consideration. So some of these things physically will not fit in the spaces we want to put them in. So that's why I have an ARM processor in my phone and not an x86 processor or a mainframe processor, right? Like size and speed, power usage is a huge one. A couple other things also, like reliability. I sometimes get asked, like, hey, can you release like a Raspberry Pi style mainframe? And I'm like, well, it's not just about the architecture for some of these, it's about everything built up around it. So in the mainframe world, we have like ridiculous amounts of redundancy on every single component in one of these machines. And even if you say, well, I'm just a hobbyist, I don't need that sort of redundancy, it's not really something we take into consideration. Like, we're going to have redundancy, that's part of the platform. And then in other ones, like that RISC-V board I have, it was not very expensive, and it's not very expensive. One of the USB ports is already not doing so well, and that's just because I got the thing for like $80 on a Maker website, right? So there is like considerations with how much cost and value there is to some of these things, and that's why we're going to have sort of this broadening of horizons with architecture. Another thing I mentioned here is tooling. So if you're developing for Android, you're probably going to find your build environments are going to be very ARM-based. And so it kind of creates like this gravity for developers, like they're going to develop for that platform because that's where the tooling is. And this is also varies by industry. So in the mainframe world, or if we're talking something like IBM Power is very traditionally like AIX. If you're thinking like the AS400, that's not a mainframe, that's Power. But these have been part of specific industries, so the tooling available to these industries are also going to gravitate towards specific architectures historically. So they may find more tooling on one rather than the other. Doesn't mean they can't change, it just means there's an amount of gravity there that keeps them there. So lots of reasons for other architectures. So the first question I had when I joined IBM, so I'm a Linux systems administrator by training. So I spent 15 years of my career, half of it in the Philadelphia area, doing like Linux sysadmin work, racking servers, putting in those x86 machines. I joined HP and started working on OpenStack. So I started doing a lot of cloud native work. I spent a little time in San Francisco working for a container startup and kind of getting further and further away from bare metal work. So after the container startup, I was like, all right, I am so over San Francisco. No, I love San Francisco, I still live in the Bay Area. But I was kind of over like fast-paced, relentless startup culture, and I was like, I want something different. So I found something different. So IBM was like, hey, you wanna work on mainframes? And I'm like, oh, no. I didn't know what they were, honestly. Like I sort of peripherally encountered them places in my career, but I didn't have a firm understanding of what they were. So essentially, they're big like compute machines. They have a ton of RAM and a ton of processor power, and they just like churn through data and then connect through external data stores. And so when they told me they run Linux, I was like, what does that mean? I understand it's another architecture, but that means you have to recompile everything. So is a Linux distribution on a mainframe every single package recompiled? Seems like a lot of work. And they were like, yep, and yes. So in a Linux distribution, when you port it to another architecture, all of your compiled packages have to be recompiled for the target architecture, which means all of the big Linux distributions, we're thinking our Red Hat, SUSE, Canonical, for Ubuntu, they have mainframes in their data centers, and that is what they build their packages on. The smaller distributions usually leverage some of that. Like my team, we've given VMs to Debian, we've given VMs to Rocky Linux, but also like the OpenSUSE community uses SUSE's mainframes. And of course the Fedora community uses Red Hat's mainframes. But these do all need to be recompiled on the architecture. If they're interpreted, the interpreter needs to be built for the architecture, so think of like Python or Node in JavaScript stuff. All you need is like the interpreter needs to work fine, and then your interpreted language will probably work fine. But yeah, it's a ton of work. So you may be saying to yourself, all right, my open source project is in a Linux distribution. That means that they've already recompiled it, and I never have to worry about it. Yay, I'm done. You can leave the talk now. All right, but I'm just going to tell you to wait a moment. Because that may be the case, maybe. But there's some things to keep in mind. So if your package is in the Linux distro, it also has to meet some certain criteria. So in distributions like Red Hat and Ubuntu, they have like different type parts of the repository. And those may not necessarily be parts that are automatically compiled for architectures that are not x86. So the first step is making sure that your repository, your software is in the repository that's being recompiled. For a long time, the EPEL repository that a lot of people use on Red Hat, which is, maintained by the Fedora community, that was not being recompiled for IBM Z. And so anyone who was running on the mainframe and wanted to use anything out of that repository, they couldn't get it unless they recompiled it themselves. So first, you have to make sure you're in that repository. Second, you need to be important enough for the developers to fix your package if it breaks in that architecture. So we're going through a release cycle right now with the Ubuntu community, and there is a GDK package that is not working. And it has the potential to hold up the release of all of Ubuntu because this one GTK package is not working on S390X. And that's a problem because what the distribution will do is they'll go upstream, like to the GTK project, they'll submit a bug and say, hey, this is broken. And then GTK will be like, okay, we are a graphical component. Do you actually need this running on the mainframe? Mainframes don't have monitors. We do a ton of X forwarding. I've never seen so much X forwarding in my life. So there's the potential for having that included and needing that component. But if it's really hard to fix, if the upstream community is not committed to fixing it, it may just be kicked out of the distribution. We had this happen with another piece of software. It was VNC client. So we use a lot of VNC server on the mainframe. That's extensively tested because we do X forwarding and we also use VNC quite a bit for accessing graphical things inside the mainframe. And so I was surprised when client stopped building and we had to pause and say, but wait, client is the one you run on your laptop to get into the mainframe and connect to the server. So is anyone actually using this? So it took to some detective work. We were willing to do it because it was an important enough package. But it turns out not only people doing ridiculous amounts of X forwarding, they're doing like daisy-chained VNC connections as well throughout machines. It's a fascinating world, and it's sometimes kind of slow because you're jumping through all these things trying to access the machine. But we had to do that analysis. And if it had been a project we weren't familiar with or something that we've never seen anyone use on the platform, it may have just been kicked out. And we're like, all right, move forward with the release. We're just going to drop this package. And then finally, even if it's an important package, if we don't have collaboration from the project and it's really hard to fix, it may actually get the axe until an executive says, no, put that package back. Someone important's using it. So it has to be easy enough for a maintainer of a distribution who is responsible for thousands of packages to say, okay, upstream's not going to play with us, but we will fix it on our own because we now have the budget to do so and we hired someone to do it. So what I'd like to implore you to do is test it in your own project yourself. So how do we do that? There's a couple of ways to go about doing this. The first way is called cross-compiling. And cross-compiling is where you have, say, an x86 machine, and you use some sort of emulation to rebuild the software for a target architecture. So QEMU is probably the most popular one. It's built into a lot of CI systems. I think GitHub Actions has some support for it, where if you just pass a specific container image, you can do some sort of cross-compiling natively in that. And that's all driven by QEMU inside of a lot of this tooling. There's also tooling like Unicorn, which is QEMU-based at the core, but it focuses more on like CPU-specific operations. So again, since I'm most familiar with it, like on the mainframe, we have like on-chip compression and decompression. We have on-chip, some of the crypto algorithms can be handled by the chip, and a few other really specialized components. That is kind of where Unicorn would come in and try to emulate some of those very specific functions. So like QEMU, you can think of as like emulation of a whole mini environment, whereas Unicorn is a lot more focused on the CPU very specifically. And then also with something like the ARM development kit, which I'll show you in a few minutes, They have their own emulation tools, so you may download an emulator that's like an emulator for an Android phone or an emulator for a watch or something, and that has their own emulation tooling in it. In some cases, it's also QEMU based. In some cases, it's something proprietary and homegrown by the company. Also, if anyone has questions, I'm happy to take questions throughout. So just put your hand up, and I'll get to you as soon as I see it. Some of the limitations, some of these might be somewhat obvious, but they're not going to include every feature of an architecture, because usually things like QEMU, they're not getting all of the information about the CPU before the CPU is released. They're playing catch up, right? They're adding features as the CPU comes out, and they need to add more support for what's happening in the emulation. It doesn't have a full environment. So I remember early days when we first got our first Raspberry Pis, like the boot environment across various ARM architectures was very different. So even though you could technically emulate the ARM architecture, there was a lot more to it than that. If you're doing any sort of boot up stuff or anything that is interacting with the disk or interacting with the network, it was harder to emulate those components. And same goes with like peripheral devices. It's harder to emulate some of that stuff. It may not even be on the roadmap for a project like QEMU to emulate some of the peripheral devices. It may just be very, strictly emulation on the architecture level rather than trying to interoperate with other things. It also may run slowly. It will run slowly. You're piping it through an entirely different instruction set, so it's not going to run as fast as if you were doing it natively. So you could also do it natively. So on something like RISC-V or Raspberry Pi, you can do things natively because you could just buy one from a website and put it on your desk and connect it to an Ethernet cable, and now you have a test system there to run. But of course, that's not going to be viable for every platform, but that may be an option for your project. One of the things that my team works on is we give out virtual machines on mainframes because I can't give mainframes out. I don't even get one. It's not fair. But we have VMs that we give out to open source projects. We have like a free VM program and then another one. But those are kind of the resources that may be available to a project. The problem is, of course, this access problem, right? You have to have a Raspberry Pi and have a RISC-V, and suddenly your desk is very, very crowded, like mine. But it also has to be well connected, right? Like I probably wouldn't, I have CircleCI running on my Raspberry Pi because it was a fun project, and now I have CircleCI running on a bunch of different things. I had a GitLab runner before that. It was just, my current project is X. But I was running things on various things that I run. But if I was running these for a real open source project, I'd have to have a pretty good internet connection to my desk at home. So you have to either put these, put your little SBC, your Raspberry Pi inside a data center, or someone just has to send you patches and you run them manually, but that's not a great experience. Additionally, the one pushback we get from a lot of projects is then you have to configure and maintain this Linux environment. Now, if you're a project that has this all like orchestrated and you have Ansible scripts to automatically add your tooling and your CI system to any architecture you're going to throw at it, wow, I am in awe. But the rest of us, we more manually maintain some of these Linux servers. And so a project will say like, Liz, it's great that you'll give me a VM, but like now I have another server in my fleet to maintain, and it's an architecture I'm not familiar with, and I don't have the people for this, and I have to convince them of the value of that. But it's a consideration for sure, especially if your environment's not so automated. And then just like, oh yeah, question.
Wondering how helpful is it if we kind of blindly cross-compile something like I have no Z architecture that I can use? Is it okay to cross-compile that? Say I have a project, project something. I compile for Intel 64 and I compile for ARM. Should I also compile? I noticed GitHub actually supports S390X. Should we just do it and not know if it actually works? Is that still helpful?
Yeah, so I'll just repeat the question for recording. The question is, you have no way of knowing if the cross-compiling that you did actually worked in an effective manner, or should you still do it? And my answer to that is yes. I would definitely encourage you to do that, even if you don't have access to the hardware and you don't know that it's going to run natively. Because what you may find is people will end up submitting bugs to your project if they're running it on that platform. And you generally won't know if they're running on the platform until they start using it. Because one of the first things that communities do, or organizations, companies, governments, whoever, they will see if an open source project supports their platform, and then they'll try it. So if there's a binary out there, you have a higher chance of someone actually trying your software in the first place. It gives you a bit of a competitive edge over some of the other projects that may be in the same space, because at least they gave it a try. And if it doesn't work, believe me, they are used to it. I spend a lot of my day in installation scripts that are assuming architectures. But just having it there is kind of like the first step. And I'll show you later, there are resources. If you do get a bug report like that and are like, I don't have a way to test this, we can help you out with that. And then the last one is I kind of touched up on, again, on the cross-compiling side, is you won't have access to every peripheral device that exists. Even if you have a mainframe in your data center, you are not going to have access to every single thing that you could plug into that. And especially in something like the ARM community or the RISC-V community, there are a lot of form factors that use these architectures. So it's not even about just peripherals. It's about like the environment these things live in. Is it a cell phone? Can you emulate any of these environments that may be in? Is it a watch that I banged against the side of the house and scratched up? There's like things that are not going to be things you could do in emulation, or even if you have access to some of the native environments, because you're not going to be able to test every permutation of the environment that thing may be in. The other thing that I would be remiss if I don't mention, but is much less of a problem these days, is making sure that there's support for your compiler or your interpreter for the language that you use. So up until recently, .NET was not built at all for pretty much any architecture except for S390X. It pretty much runs on, it does run on ARM and Power and Z now, but it doesn't run on RISC-V. But other than that, Python, C, JavaScript, most of the languages, Rust, we're using these days, they will run across a bunch of architectures, but it's just, you want to check for that first. I gave a talk somewhat similar to this in Pasadena, California recently, and the keynote speaker was talking about this brand new language, and I was like, oh no, I'm telling everyone it's fine, but this language probably doesn't run on Z. So the first thing is to check is, make sure your language actually does have an interpreter or compiler, but if you're using any language that's been around for a while, you probably won't have to worry about that. The other thing is whether you're using hardware-specific features, or if you're using something like a GPU, there are no GPUs for RISC-V that really interoperate well. You can't put a GPU in a mainframe today, they're not compatible technologies. And so you have to consider what you're using in your environment, what your project is using and leveraging. Also things like I mentioned, like compression and decompression and cryptography. Some of the AI machine learning stuff that's starting to be built into the chips. So Z has one in our latest chip that comes in the mainframe. NVIDIA has ones, Intel has built-in things. So if your project leverages any of those to a great extent, you may find that your code's not going to work when you port it to something that doesn't have those features. Numbers are going to be a problem too, because different architectures handle memory addressing differently. I mentioned big endian and little endian and endianness. We find it with sorting lists and things, and when you stash things in memory, they don't come out the way you want them to sometimes. Signed and unsigned integers, they can trip you up because of how architectures handle them or make assumptions about them. Some of them don't really like unsigned integers at all. And so just some of these little things that are going to trip you up. Fortunately, for pretty much all the architectures, you will find documentation if you do run into these problems. And these problems tend to be lower level. So if you're writing something in Python, it's probably just going to run fine everywhere. If you're writing something in C or Rust, you may run into a few more problems. But it's just something to consider. And don't let this dissuade you from porting your C application. It'll probably be fine too. So I have now convinced you to port all your open source projects to all the architectures. So what is available here? So this list is not comprehensive. It is also in alphabetical order. But these are kind of having worked in the open source world for a very long time and now working as someone who ports things for a living, these are a lot of the CI systems that I tend to see in open source projects today. I'm not going to go through every single thing on this list because that would be boring, but I will explain briefly like what each of these mean. So when I say hosted, that means there is an organization that has a hosted environment to support it. So if you see on this list, ARM is doing quite well. For Circle CI, the GitLab's like free community edition they have online, GitHub Actions. There are a bunch of hosted environments that are available. So in these cases, it's pretty much just a matter of flipping a switch or updating a config file, adding a builder, whatever tooling they have for doing that. It's a pretty easy thing. In the case of self-hosted, that means you have to have a VM or some sort of environment available where you install the runner, and then you can go from there and run it yourself. So in the case of something like let's pick GitLab. So GitLab has self-hosted options. So GitLab releases binaries for S390X. You can install them on an S390X VM that I give you, and then you can run your tests on that. When I say self-hosted unofficial, like under GitHub Actions here, GitHub Actions runner is open source, but GitHub does not release an S390X version or a Power version. So there's a patch out there that we've written, that IBM has written, that you can patch the software and then you can run the self-host runner, but it's like not official and it's very manual. That's a project I'm working on too. And then like in the case of Jenkins, there is a hosted environment for Z and Power, but it's hosted at the Oregon State University Open Source Lab. So it's not run by like the company or the organization that that runs Jenkins, but there are hosting options available. The RISC-V column looks a little sad, but RISC-V is relatively new, and I left it blank so I can fill it in later, because someday we'll have a bunch of hosted options for that. So if you're using any of these projects, you can come back to the slide later and say like, okay, I know what I need to do. The other thing I recommend is, I mentioned there's an Ubuntu release coming up. There are only a few people at Canonical working on an architecture. And so when the release manager comes to you and says, hey, these things are broken on your architecture, you need to fix them, that can be a bad day. It can also feel very isolating and being like, I'm the only one in the whole world who cares about this architecture, especially if you're a little detached from the users. And now someone from the release team's like, we need to get this out and you're holding us up and you're the only one who can fix it. So one of the things that we did in the mainframe community is we created this Linux distributions working group. And it's something I think anyone here who's interested in porting their software can leverage as well. But we pretty much get together on a monthly basis. We also have a mailing list. And we work through any issues that are going to be hitting all the projects. So the issues I mentioned before, like BNC client or the GTK issue, these are problems with open source projects, and they're going to hit all the distributions. So we all get together and say, how are we going to handle this? Or if a project is considering dropping support for an architecture, we're like, all right, we got to get together and show them that there is a user base and show them that there's demand for this and demonstrate to the community that there is a need. And so that's what the working group does. So this is just very specifically to mainframe, but other communities have this, which I'll get into when I talk about the resources. But in general, maybe finding someone else in your project who cares about architectures as much as I do, or is like wants to geek out on some things with you. Just finding a peer to sort of help you out has been really beneficial to our community, at least. So let me see what the timing is looking like. Oh, I'm doing fine. So developer resources. I'm just going to go through these. If you're interested in a specific one, I got the QR code to the link. And then if you, I'll make the slides available as well, so you can check those out later. So in the ARM community, as far as developer resources go, they have a bunch of documentation, they have training videos, like learning paths and blogs and forums and all kinds of things for community engagement. I mentioned some emulation software being developed by a community. So in the case, ARM has an ARM Development Studio, which you can download, and that emulates a bunch of different environments for various development you may want to do on ARM. IBM Z, so we give free native access to S390X VMs. There's two different programs for this. There's one that's open to anyone. Like today, you could go get a Linux on Z mainframe environment and SSH into it without even talking to a human. You just fill out a form. But we also have an open source program. So if you're an open source project, you can apply to the program. And honestly, I let as many people into that program as possible. As long as you have an active open source project that's not doing nefarious things, I want to welcome you into our community, and I'll give you a VM. Those VMs, so the free ones last like 120 days. The ones that are part of the program, they're renewed annually. So every year you'll get an email and say, hey, are you still there? Are you still doing development? And if you say yes, then we'll keep you going. You might get an email from me every now and then, just checking in, making sure you don't need any help. But otherwise, they're like permanent VMs, essentially, for your community. And then I linked to a bunch of CI systems from that chart that also support the platform. IBM Power and Open Power. IBM open sourced the architecture for Power a while back, or the ISA. And so now there's the Open Power Foundation. So there are several programs out there now, some of them from Open Power, some of them from IBM. But this link and this QR code here will show you what programs are available. Some of them are for companies, some of them are free resources for open source projects. Very similar to Z, where you get a VM or there's like training and instructions and other things. But the Open Power Hub is pretty great because they show you access to all these resources you can get. RISC-V, they have a development community, and you can apply to get RISC-V boards. And it's not just for open source projects, but open source projects certainly will qualify if you can make your case and submit your application. And then you can get one of these, like, the Vision 5.2 that I have, or another a small device to start doing testing on your open source project. And they have, the RISC-V community has forums and chat, mailing lists, documentation, things that pretty much all these communities have. All right, and I have come to the end. So, anyone have questions? Yeah.
That makes people know my ignorance, but so you said IBM has, you can get IBM Z VMs. Is there an advantage to running an IBM Z VM on mainframes versus having like the QEMU run IBM Z?
Yeah, I mean, it's pretty much, QEMU is not going to have all of the permutations of every weird, quirky thing that may happen with the architecture. So you don't necessarily know it's going to run really well unless you test it on native hardware. So emulation is just always going to lag a little bit. So when you can, testing it natively is going to be great. But if if it's easier, most projects start with cross-compiling. And then if they get a couple bug reports that the cross-compiling is missing, that's kind of when they take the next step and say, all right, I need a real VM. And even if they don't add that VM to their CI system, a lot of developers just use it. Like, I'm happy to give a VM to a project who just wants to use it for like one developer who's going to test all the broken stuff on it, right? Like, they're like, oh, this is not being caught by QEMU, but I can test it manually on the machine. So in that case, there is a benefit to running it natively rather than under emulation. Or if you do want to add it to your CI system, and you're doing, you want it to be faster, it's going to be faster on one of these virtual machines than it usually would be with cross-compiling. Yeah?
Is there a market for IBM Z virtual servers like you can get for x86?
I don't know a lot about that. I know we sell them in IBM Cloud. So there's a couple of different products. There's like a HyperProtect product, which is very security-based, and there's VMs in that product. And then there is just like the IBM Z virtual machine product. I don't actually know what that market looks like or anything on that side, but they exist. So presumably someone at IBM thinks there is a market there, but it's only on IBM Cloud as far as I know right now. So, yeah.
Do you have
Yeah, so the question is go-to tricks for compiling in a cross-compiled environment on S390X. It's going to depend on your language and your environment and a whole bunch of things. But usually what I do, because I work on so many different languages these days that I can't keep them straight in my head anymore, so I always have to look at the documentation, honestly. So based on various languages, I can usually give me 5 minutes and I can answer your question for a very specific thing, but I don't keep them in my head anymore. But there are ways, and we are putting together actually right now some guidance for troubleshooting on specific languages that come up a lot. Especially around endianness is pretty well covered, but the QEMU environment where you are passing different flags, that's kind of under-documented for certain architectures. So, yeah.
Roughly how many mainframes does IBM sell in a year, and how long do they last?
How many mainframes does IBM sell in a year, and how long do they last? I don't know. The market is growing, I will say, especially in the Linux side. So we have Linux-only mainframes as well. They're called Linux One. I got to see one the other day too. That was cool. But that market is growing faster. It's growing. So I don't know how many there are, but there are more rather than fewer, which is what I think a lot of people assume, and I did before I joined. And then what was the other part of that question? That was. How long do they last? How do I say this without getting into trouble? Okay, we release a new one every 2 to 3 years, and we strongly encourage you upgrade. Realistically, I think on the test floor, I think officially they are supported through IBM support for something like 8 years, maybe. But it's n minus a certain number. I don't remember exactly. But yeah.
All right, let's have a big thank you to Elizabeth for presenting today.